So welcome everyone. Today I'm gonna cover topic machine learning based low cycle fatigue techniques for reinforcing bars. I know it's ACI, but reinforcement is part of the concrete. So our research is to come up with new ways with machine learning to predict the low cycle fatigue of reinforcing bar. I'm presenting on behalf of my student Naga and myself. I'm an assistant professor at Rowan University. So if you are familiar with low cycle fatigue for reinforced bars, we start with recording the strain cycles. We have to do number of counting for cycles. We can use rain flow. After that, we use empirical equation like Mander models. And after that, damage rolls to get to the fracture of reinforcing bar. So it's a long process, and our objective is to try to bridge the first to the last. So how can we predict the damage of the rebar in concrete just from the strain cycles, nothing else. So I'm gonna present a background on this. This is not working. So this is actually Dr. John Stanton here. It's just a coincidence. So I did my PhD at University of Nevada, Reno, with collaboration with University of Washington in Seattle. And this project was to test larger scale specimen where we build rocking columns. Well, a specimen was 72 feet long, and we have opportunity to get estimation of a strain until fracture. So this is a specimen where we have a pre-tension columns, and the pre-tension columns connected to the base using socket connections that developed at University of Washington, Seattle, and top connection, that's hybrid connections. You can see the rebar and the debonded length using the red duct tape that also developed at University of Washington, Seattle. So this is the big specimen that we tested at University of Nevada, Reno. This is me like 8 years ago. And this, I don't know if you see if there is a sound system here or not, but you will hear a lot of sound of fractures as we tested. So the column rocks back and forth. And if you zoom in, you will see it rocks at the top and bottom connections. And here where we actually get some strains, like high strains in the rebar, and eventually fractured. So yeah, you can see here the zoom in rebar. You can see it's a rocking column, so at this interfaces, it's open up, you don't get the rebar, induce strains, and fracture eventually. We have one challenge that we were not able to visually inspect the reinforcement because, as you can see here, almost no damage to concrete. So we came up with different ways to estimate the reinforcing bar fracture. So the first damage, as you can see, is just a damage stage comparison between this system and the conventional system. We only have one hairline crack at 13% drift ratio. We have some steel tube that we used at the end to confine the concrete to prevent it from crushing and spalling. And we have some buckling or bulging of these tubes, which can be adjusted as if you have if you can have some stiffeners. But we have an issue, actually, that the rebar was inside and the rebar is fracturing, and we were not able to actually evaluate the rebar fracture. I don't know, you hear, so it's just good news. So this is one connection that we tested. I don't know if you notice the sounds of fractures. We have a total of 72 bars in this bridge, debonded. I have another video with I did slow motion to isolate those sounds so you can hear. So those clicks are the bar fractures that happen during some of the ground motion, the high intensity ones. So the first thing that we did is we did acoustic emissions to identify where is the noise, because we are in lab, there is so many noise. So we identify the threshold for the noise, and after that we decided, we have a lot of work on acoustic emission where we isolated and find out per motion how many bars fractures. But we have another actual advantage of the system in a strain estimation side, that due to the rocking motion that we have, you can actually calculate, we measured all the rotation of the joints, so we were able actually from those rotation to get the elongation on the rebar, and because the rebar is debonded, we actually be able to get the strain equivalents to those in the rebar. Because when we use the strain gauges was damaged actually way before the fracture of rebar. So here you can see the comparison between the strain gauges that we put in here in red dotted, and from the rotation of the joints at, I think, one motion that we were able to capture the strain from strain gauges. So we use this strain from displacement to actually to use all histories of those strains up to failure. We used different techniques. The first technique I mentioned was to get the strain, and after that, with all this processing that we did, and after that we did actually calculate number of cycles using low cycle fatigue. First, rain flow algorithm. Second is using fatigue equation from Mander. And after that, we use Menor rule to get the accumulated damage of the rebar. And we keep adding the next ground motion to find if it's damaged or not. If it's past 1, it's damaged. If past, it's below 1, it's not damaged. And this is some graph that we showed, motion 15, 16, 17, 18, how much they damage, accumulated fatigue damage index. And once you get 100%, you actually damaged the rebar. And here is just a comparison between acoustic and low cycle fatigue. So all of what I presented is work done in 2014-15 during this project when I was doing my PhD. So what we did now is, based on this data that we have 72 bars, we have 24 ground motion, we focus on the high intensity ones. Will we be able to predict the fracture of rebar just from the strain data or not? So not going through the low cycle fatigue analysis, no rain flow counting, no damage models, or no empirical equation. So we have this technique that we used before is, we use CNN. So the first one you can see here, we have the strain of reinforcing bars. We were able to use MTF technique to convert this to an image. And from an image, we actually created CNN model to predict if the bar fractured or not. So I'm gonna dive deep on the technique that we used. So basically in time series, if you wanna use time series data in CNN, people are using either images for detection, other used the time series, reorganize it in 2D image, other use histograms. But the problem with this, that always neglect the temporal effect. So when the strain happened, because in a low cycle fatigue, you also worry about the history of the strains. So what we did is, this is a technique. One of them is the GAF, German Angular Field. The other one we used is MTF. So basically, any time series data, you can represent it with an image. So this is, I don't know, we have another one here. In some cases, we do have noises, because let's say we have a rebar that fracture after a time, but we need to train to the end of the ground motion, so we use those noises, very low amplitude ones, to actually convert it to an image. And you're gonna get more information on the structure of CNN in this following slide. So this is just how to divide the data from damage, no damage, and which ground motion and which connection in the bridge. So this is very detailed, and it's in some papers that hopefully will be published soon. So here is the meat of the presentation. So what we did is here, let's say you have a ground motion, one of the ground motion, the first one. And you know that the rebar is not fractured. And you know you have around 20 ground motion that is back to back. So what we did is, in this case, the bar is not fractured. What we do, we have multi-input layers. We put the strain gauge or the strain data for the first image. And after that, we assume no ground motion happened to the end, and we use the noise data for all the other channels. So you can actually keep stacking images until you have a fractured bar. Let's say this bar fracture at motion number 4. So you keep putting the history of all the images, and after that, you keep adding white noise or the small noise data at the end. So we end up having very nice training data based on my PhD testing. So training was almost 100%. In the testing side, we actually don't focus mainly on accuracy. We focus on F1 score because the data was skewed. So you have so many information about undamaged, but less in damage. So the data is 90% and 10%. So we used F1 score. So you can see here, F1 scores out of 1, you range from 0.99 to 0.93. So I always, when I teach machine learning, I would say accuracy is a kind of fake measure because you may have 90% of or 95% of data as one class, 5% in other class, and if you got 95%, you think it's good, which actually missed maybe a 5%. So the vision here, what's next is any system, this is not applied to my system. If you develop a new system, you can do larger scaling, you can identify damage, you can do calibration from numerical models, you can scale up the models, get an equivalent strain data or equivalent acceleration data or drift data, because the method is applying to every time series. And after that, you can train the models to predict your acceleration, drift, or in this case, was low cycle fatigue. This is the conclusion we have. The multi-channel input was actually using CNN was powerful with accuracy or F1 score, higher F1 score than we expected actually. So the low noise strain that we used actually was capable of balancing this input file, input layer. Number 3, we actually have a very simple CNN, only 3 layers. So it's not deep in a sense. And we were able for first time to predict the fracture of rebar based solely on strain data without rain flow counting or damage models. And we are looking forward in future to test different bar sizes, different bar grades, and different even materials with low cycle fatigue and this technique to predict the fracture. This project was funded by a grant from ABC UTC or USDOT through ABC UTC. So thank you very much for attending, and I'm ready for any questions.